Hello, my name is Neil Valam, and today I'm going to be presenting my project on predicting diabetes with logistic regression. Before I begin, I'd just like to present the overview of this presentation. So first, I will begin by overviewing the project and its goals. I will overview the data set, and then I'm going to give a summary on the paper, as well as a summary on the coding structure and organization. And then I'm going to go ahead and present the code and do a quick overview. And then I'm going to go ahead and demonstrate the code. Um, and then to incorporate aspects of the paper, I'm going to go ahead and demonstrate the results of the code with the experimental trials. And finally, I'm going to go ahead and discuss areas of future improvement. And right after that, I'm going to give my final thoughts on the project. So just really quickly, the overview of this project. Um, the goal of this project was to create a program that predicts diabetes diagnoses based on several risk factors that can be found from the data set, which I'll be introducing very soon. And to implement this goal, first, we want to find the optimal coefficients using Newton's method for each of the risk factors, sigmoid function. And then the code is going to go ahead and allow the user to enter different factors, otherwise known as weights, that will be plugged into each sigmoid function, uh, incorporating the calculated coefficients. And then finally, it's going to go ahead and return the probability. So as mentioned, here's the data set. I'm going to really quickly do an overview of the data set. So this data set is titled Pima Indians Diabetes Database. It's a portion of data collected by the National Institute of Diabetes and Digestive Kidney Diseases. The data set goes over multiple risk factors among females aged 21 plus in the Pima Indians Diabetes Database. In total, there were 768 participants, and this very briefly overviews the data points. So for example, we have number of pregnancies, with most of the participants leaning towards 0 to 1.70. We have the average glucose, which is fairly normally distributed, as well as blood pressure, which is also fairly distributed, with an outlier at 0. Then we have skin thickness, which is measured in millimeters, insulin, which is skewed more to the left, with most participants having 0 insulin. And then we have BMI, which is relatively normally distributed with an average of around 26 to 33. We have a diabetes pedigree, which most participants leaned more to the left, with the average being around 0 to 0.31, as well as age, with most participants being in the range of 21 to 27. And finally, the outcome, which is either 0, indicating that the participant does not have diabetes, or 1, indicating that the participant does have diabetes. So to give you guys a better idea of what the data looks like, I'm just going to go ahead and pick a participant by random. So this particular participant had 5 different pregnancies. Their glucose level was at 166. Their blood pressure was at 72. Skin thickness at 19 millimeters. Insulin at 175. BMI of 25.8. A diabetes pedigree function of 0.587, and their age is 51. And let's see if they had diabetes. So it looks like they did. So the overall function, or goal, I should say, of this project was to take all of these data points, which is downloaded in a CSV file, and implement them into my code, to have them go through various logistic regression functions, including the Newton's method, which uses, a log likelihood, which is used from a sigmoid function, and this returns the coefficients that are going to be used within the sigmoid function when the user wants to enter certain weights or risk factors. I'll go over this a little bit more in detail in a future part of the presentation. This part was just to show what the data looked like. So moving on, I'm going to go ahead and do an overview of the paper. So this is the research paper that I've created based on the implementation of this project. So instead of going through every single part, I'm just going to read out the abstract just to give you guys an idea of what the paper illustrated. So the paper describes a proposed predictive model intended to evaluate the probability a patient can be diagnosed with diabetes. The statistical theorem used to create the model is logistic regression. Data it uses, as mentioned, generates predictions from the Pima Indian uh, diabetes database. The data, also as mentioned, includes a group of uh, Pima Indian females aged 21 or more. This is something that I didn't mention in detail before, which is that the measurements recorded are as followed: pregnancies, glucose level, blood pressure, skin thickness, insulin levels, BMI, and the diabetes pedigree function, as well as age. And so the rest of the paper showcases the program, which is coded in Java using both Java and JavaFX libraries. So I use JavaFX for the UI implementation, which I will very shortly introduce and go over. But for this part, it is programmed in object-oriented style with six different classes and various helper methods. It has a running time of worst case scenario of O of n. The program outputs the average of 8 different probabilities inserted into sigmoid functions with coefficients calculated through logistic regression methods. The program has a 93% success rate with a threshold of 50% and 20% success rate with a high scrutiny threshold of 90%. This paper evaluates the need for different machine learning methods paired with logistic regression in future studies to ensure better accuracy in predicting diabetes diagnoses. It also recommends the use of datasets with more diverse demographics as the result of this paper is limited to females age 21 or more in the Pima Indian community. So I'm just going to very briefly go over the structure of the paper. So first we have the introduction as well as the related work. We have the methodology, which introduces the data set which has been used. And then it goes over the machine learning methods, which is binary logistic regression. So basically the logistic regression model that we've learned about in this class, the binary just indicating whether the outcome is either a 0 or a 1. So in other words, there's going to only be two outcomes, a success or an unsuccess. It's going to go ahead and use a logit function, which is essentially a sigmoid function, but a sigmoid function is formatted a little bit differently. And this is just the math behind it. Then here we have the actual sigmoid function, the log likelihood function, as well as the mathematical theorem behind it. The Newton-Raphson method. Oh, sorry about that. With also with the mathematical theorem explaining it. It's going to the Newton method is going to utilize the Hessian matrix as well as the gradient. And so the rest of the paper, or the methodology, I should say, goes over the coding structure, which I will go ahead and present now in the slideshow. So this isn't the best picture. Okay, here we go. So this is the overall structure of the code, summarized in a pretty simple fashion. So the front end of the code is going to have a panel where the user can insert different risk factors, and the back end, which the user will not be able to see, will read from a CSV file, which is the CSV file of the data set that I just introduced. And it inserts all the attributes of the CSV file into a list, which is created in the program. It takes these and implements it into Newton's method, and it inserts user input to the sigmoid function, which uses coefficients outputted by the Newton's method, And then finally, it returns the average of all of the probabilities. So in this case, since there's 9 data points, with one of them being the outcome, there are 8 different risk factors or data points, which are averaged together and returned for the user to see. And I'm going to go ahead and just show this part of the slide just so you can see the full image. So this is basically just a class diagram of the code. Obviously, you would start with the main class, and then the main class calls a different class and its function parse file, which calls various different classes. So it calls the subject constructor as well as the subject constructor with arguments of the subject class, as well as it calls the create vectors method of the vector class. And then from here, sorry about that. And then from here, the functions within the vector class ultimately call the log regression class, which is responsible for all the sigmoid, log, likelihood, gradient, Hessian, and Newton methods that are required to implement this project. And then finally, it excuse me, it enables the calculate function of the main scene controller, which is the class that implements the various methods and functionalities of the user interface. And finally, show calculations is called, which basically shows the user the average of all of the probabilities output by log regression return outputs. So right now I'm just going to go ahead and do an overview of the code as well as do a demonstration of the code. So allow me to just present Eclipse. Just make sure it's within the window. Okay, there we go. So as mentioned, we start with the main class. So the main class uses JavaFX to create the stage, and then the main method calls the parse file function of the parse class, which I'll go over in a little bit. But before it does that, or rather, I should say, after it does that, it launches the stage which is created, which is called the main screen at fxml. So I utilized a application called Scene Builder to create the user interface as well as the various method and object names that were assigned to each object in this fxml file. And so this made it much easier to create the user interface as well as incorporate it into the rest of the code using JavaFX. So I'm just going to go ahead and close that really quickly. So as mentioned, it calls the parse file method of the parse class. I'm going to go ahead and open up the parse class just to show you what is going on there. So the parse class reads data from the CSV file, diabetes.csv, which is the data set using all of the data points that is used in this application. So it reads everything. It initializes an array called store array, which basically inserts into the array each risk factor in each line of the CSV file. So let me just really quickly demonstrate that. Let's see. Okay, so this is a CSV file which was used in the implementation of the program. So store array 0, for example, stores the amount of pregnancies. Store array 1 stores the glucose. Store array 2 stores the blood pressure, and so on and so forth. And it keeps on doing this, and all of these points are inserted into a main array called subjects, which implements the subject class, which I'll introduce in just a bit. But it stores each line into each data point of the subjects class, and as the name could tell, the subject's object is indicative of one subject or participant in the study. And so after that process is done for one subject, it initializes all the store arrays back into its original null variables. And of course, to execute the loop, we increment I, and then we increment j, and then it closes the buffer reader just to avoid memory leaks. And then it calls create vectors of the vector class, which I will show right after showing the subject class. So this is the subject class. Subject class is pretty much indicative of each participant. So each participant has 8 different risk factors. And so just to avoid calling a name or a variable for each of the factors and simplifying it down, I've just created an array of factors, and each index represents a different risk factor. So for example, factor 0 indicates pregnancy, factor 1 indicates glucose, and so on and so forth. And so the only constructors that are called in this application is the subject constructor with the respective arguments. I did create a default constructor just in case. And then there is a print function, which in this current implementation of the program is unused, but I created it just in case as well as for debugging purposes. And then finally, there is a public method called getFactor, which which returns the data point for at a certain factor. So for example, in another class, if getFactor0 is called, it'll return the factor 0, which is pregnancy for this particular subject. And so if I just go back to parse, subjects is a new subject array of size size of the data point, so how many participants there are. And in each subjects, as mentioned, is added each line of the CSV file. So all of that subject's attributes, such as pregnancies, blood pressure, so on and so forth, is stored within the subject class that represents that subject or participant. And so just going down the code, finally, it calls v, which is a object of the class vector, dot create vectors. So let me just navigate to the vector class. So this is the vector class. It first starts by initializing a list of vectors called list, and then it also has a list of vectors called factor data. So these are just a group of 8 different vectors that each represent the risk factor for each data point in the study. And then finally, it has a static double array, a 2-dimensional double array called coefs. So this is just used to store the coefficients that are returned by the bulk of the log regression class, which I will get to in a bit. And so as mentioned, the parse class calls the create vectors method, which calls the create outcome vector. So this essentially just creates the vector for the outcomes. So for example, let's just say the outcomes are 0, 1, 0, 1, so on and so forth. This vector adds all of those data points to the vector outcomes. And so after this, for int I equals 0 until I is less than 8, so for for 8 different iterations, it calls the make vector method. And so this basically just stores each and every risk factor into the factor data vector at a certain index. So as mentioned, index 0 is indicative of pregnancies, 1 is indicative of blood pressure, so on and so forth. And then after all of that is called, a separate list is called make separate vectors. And so this basically just separates the vectors that are indicative of a 0 outcome or a 1 outcome. Now, while this particular method is not used in this implementation of the project, I did think that it would be useful to create something like this, so I've added it. And then finally, there are several print methods And again, since it is not since they are not required for the user to see, they're simply just there to output the results of each iteration. I've added them for the sake of debugging um, and for the sake of future use. So that is the vector. Oh, sorry, I forgot to mention. So after that, it initializes 8 different um, log regression objects. And so each of these log regression objects calls in the object a get coefficients excuse me, method, which I will present very shortly. Um, Ignore this. This is all for debugging. Should probably change that to 0 actually. So the print statements are for the sake of debugging, and this is actually what you see over here. And so the function of this is to return the coefficients that are going to be used in the sigmoid function, which I will now explain. So let's go over to one of the final classes of this program, log regression.java. So this program is a little bit more complicated, so I'll be thorough in explaining it. So first and foremost, it initializes a private double array of coefficients, which will store each coefficient for each sigmoid function, a vector for factor and a vector for the outcome. And so when the class is called, or excuse me, when the class is constructed, I should say, it takes several different arguments. The first being the vector of factors, the second being the vector of outcomes. The second and third are the initialized estimated coefficients that are used. And so this is just returning the coefficients, but that's pretty much the last thing that this class will do. The first thing it'll do is call the Newton's method with the factor and the outcome. So 2 different vectors. So if you navigate down to the Newton's method, um, it initializes various variables such as coefficient g, which is the array used to store the gradient, g underscore t, which is a transpose of the gradient vector, dot, which is the array representing the dot product of the Hessian, which I'll explain in a bit, the inverted Hessian and the transposed gradient. There are 2 coefficient values which are used based on the coefficients that the user provides to initialize the process of finding the optimal coefficients. Updated C1, updated C2, I'll show you guys in a bit just what that is going to do. Delta L, convergence, so max convergence, and all the other data points, which won't make as much sense until I actually explain the bulk of the method. So I'll just go ahead and do that. So Newton's method, let me go ahead and to show the mathematical overview of Newton's method really quickly. So Newton's method essentially adds to a certain data point, in this case, a coefficient based on the previous coefficient. So let's say we're at iteration t, it returns the coefficient at t minus 1, and it adds it by itself plus plus the final matrix that we get over here. So oh, sorry, this is the gradient matrix. So the gradient matrix transposed times the Hessian matrix inverted. So minus x transposed times w, matrix w times matrix x. And so this part of the code intends to do just that. So it first initializes a while loop, which will run until the delta H, or the change in the log likelihood from the previous iteration to this current iteration, is greater than the convergence which we have set at 0.01. And it'll run until I is less than a number of max iterations, just so the loop doesn't run at a redundant amount of times and crash the program. Obviously, I is iterated so that the loop can function as needed. And so G is the two-dimensional array, double array that we've created over here. So G is set to the gradient function, which if we just navigate a little bit higher, we find that the gradient function is the gradient of each of the sigmoid probabilities. So that calls the function sigmoid, which if you go over here, essentially takes the vector of the risk, so pregnancy, blood pressure, and so on and so forth, takes the coefficients, and essentially it returns the sigmoid function, and it stores it in a vector called sigmoid vector, and it returns that. So gradient taking that vector, it creates a left-hand side and a right-hand side sum. So basically just the first gradient variable and the second gradient variable, and then it returns it and stores it in an array called gradient, a two-dimensional array called gradient. And so after gradient is returned, the program transposes it in a function called transpose, which essentially sets the columns as rows or rows as columns, or vice versa. And then H is initialized to be Hessian, so it calls the assign method, which takes risk, outcome, coefficient, and coefficient 2. And so if we go to the Hessian method, it essentially does a similar thing as a gradient. However, now there are 4 different outputs. So this is essentially just the sigmoid probability at a certain index times 1 minus the sigmoid probability at a certain index times coefficient 1 times coefficient 2 for D1, coefficient 1 times 1, and 1 times 1 for D2 and D3. These are summed up by the sigmoid prob size. So for the size of the amount of participants in the study. Finally, it outputs the Hessian array, which is used over here and inverted and stored in a variable called H underscore inv, or H inverted, excuse me, for short. And so the invert method, excuse me, essentially does just that. It inverts the array and returns it. And so after that is called, we take the dot product of both. So of the transposed gradient as well as the inverted Hessian. Update C1 and C2 are 2 different double variables that are assigned to the dot product of both variants. And then coefficient 1 and coefficient 2, which was initially initialized as estimated coefficient 1 and estimated coefficient 2, are added to by the update C1 and update C2. LH updated is equal to the log likelihood, which I'm going to explain just now. So the log likelihood is similar to the other functions, however, it differs in that it calculates the sum of the outcome times sig, which basically just means the log of the sigmoid prob at a certain index plus 1 minus outcome times sig1, which is the output of the sigmoid prob at a certain index. The log of 1 minus the log of a sigmoid at a certain index. So that is the basic overview of the code. I'm just going to go ahead and run it now. So here is the diabetes prediction calculator. Since I am short on time, I am just going to run one trial of, the first participant in one trial. So let me just go there really quickly. Let's see. Let's just choose at random. So participant 266. So that individual has 5 pregnancies, 96 glucose, 74, 18 millimeters, 67 insulin. a BMI of 33.6, a diabetes high degree function of 0.97, age 43, and we're going to see the probability, which is 25% probability of having diabetes. And as the actual database indicates, which the outcome is 0, this individual does not have diabetes, and the program that I've created says that this individual has a 25% chance of diabetes, which is below the 50% threshold, which indicates a success. So just for sake of time, I'm going to go ahead and give my final thoughts on the program. So my final thoughts are that this program is a reasonable estimate of predicting diabetes in users. However, it is not an extremely accurate program. It is a reasonably accurate program with 14 out of 15 different trials having shown success in that it is below or above the 50% threshold, depending on the outcome. Now, there are, of course, areas of improvement. So first and foremost, it is useful to use other methods than just logistic regression, maybe even other machine learning methods alongside logistic regression. Secondly, the data set that was used was limited to females aged 21 plus in the Pima Indian community, and it wasn't a demographically diverse data set, and that would help in reducing variability. And on the topic of variability, I think there are different methods that can be implemented to account for outliers and extreme variability that can sometimes be seen in the data set that we have used. So I think that if future studies touch upon these areas of improvement, it can create a program that is more accurate at predicting diabetes than the one I've created. And so that is it for the presentation. I thank you very much for watching and listening, and I hope you enjoyed. Thank you very much, and have a good night.